Hello and welcome to the presentation of our paper, Order in the Court, Explainable AI Methods Prone to Disagreement by Michael Neely, Stefan Schouten, Maurits Bleeker, and Anna Lucic. We are all associated with the Informatics Institute of the University of Amsterdam. I'm Michael, and I will be co-hosting this presentation with my co-author, Stefan. We have three goals in this presentation. Our first goal is to explain a recent paradigm in explainable AI that we call agreement as evaluation. Our second goal is to describe how this paradigm has been used in the related literature. And our third and final goal is to explain our research. In our research, we highlight the flaws with this paradigm and argue that it should no longer be used to measure the quality of feature additive explainability methods. Explainable AI is a broad and complex field with the general goal of making black box models transparent by explaining their predictions. Perhaps the two most important properties of explanations are that they are A, faithful to the model's reasoning process, and B, plausible to human stakeholders. There are multiple categories of post hoc methods to generate explanations, but the ones we focus on in this presentation are of the feature additive variety. These methods quantify the salience or importance of each input feature towards a model's decision. In this presentation and in our paper, we refer to feature additive explainable AI methods as just XAI methods. There's been an interesting development in the natural language processing community over the last few years, and that is interpreting the attention mechanism, which is used in many NLP models to explain the decisions of the model as a whole. Broadly speaking, the attention mechanism builds a context vector to weigh the relevance of different input regions. This process means that attention can be viewed as an XAI method because the attention weights might, and I say might because this is an active area of debate, represent the importance of input features. It's worth considering attention as an XAI method because it comes with several advantages. It is highly plausible, particularly when the weights are visualized as heat maps. It is also efficient since it's already baked into the model, and it's also potentially faithful as well, since it is trained with the model and improves predictive power. The attention mechanism went undisputed as a method for interpretability for about 5 years, from its introduction in 2014 until 2019, when Jane and Wallace argued in a highly influential paper that attention is not explanation. In their work, they argued that, should attention be a valid form of explanation, it must satisfy two properties. Our work is inspired by their second property, that attention weights should correlate, or what we call agree, with other XAI methods. Let's look at an example of what agreement looks like. Here we have three XAI methods, LIME, feature ablation, and attention, applied to a binary sentiment classification task on this movie review. We can treat the feature importance scores of each input token as a position in a ranked list, and then calculate the correlation between the rankings. In this example, LIME and feature ablation correlate, or agree, far more with each other than either method does with attention. If this pattern consistently holds across many examples, then Jane and Wallace would say that attention is not explanation, at least under their second property. This paradigm is gaining popularity in the literature. It has been used to invalidate both vanilla and sparse attention, as well as to justify alternate analyses of the attention mechanism. We include two different examples of papers that have presented increased agreement between XAI methods and their particular modification to the attention mechanism as proof that their methods are more faithful. As the popularity of agreement as evaluation grows, it's worth examining whether this paradigm is actually appropriate. This paradigm makes a key assumption, that XAI methods can act as standards for their peers. But it might not be appropriate to expect XAI methods to agree with each other, particularly since these methods are context-specific and since their performance varies depending on the diagnostic test considered. For a more accurate assessment of this paradigm's validity, we need to hold all XAI methods to the same standard. The previous papers we discussed all compare XAI methods and attention, but there hasn't been a comprehensive study of how well these methods agree in the first place. To remedy this, we expanded the original method of Jane and Wallace to include more models, more tasks, and more modern XAI methods. We asked, how well do the XAI methods LIME, integrated gradients, deep lift, GradShap, and DeepShap correlate one with each other and 2 with attention-based explanations. Does the correlation depend on A, the model architecture, or B, the nature of the classification task?
The way we answer this question is as follows. For each model prediction, we calculate a vector of importance scores, one for each of the model's input tokens. We interpret these scores as a ranking and calculate their similarity using the Kendall-Tau correlation metric. We then calculate the average Kendall-Tau correlation between each pair of explainable AI methods. We do this for 3 randomly sampled subsets of 500 instances each. This method is employed in a number of configurations. We use 2 models, a BiLSTM and a Distilbert. For the Distilbert model, we use attention rollout to obtain token level attribution of the model's predictions. We have 2 kinds of tasks, single sequence and pair sequence classification, and we have 5 datasets between them. In our experiments, we include line, integrated gradients, and deep lift, as well as 2 SHAP approximations, GradSHAP and DeepSHAP. For each model and task combination, and each pair of explainable AI methods, we obtain an average Kendall-Tau correlation, which gives us the following results. Here we can see a compressed overview of the Kendall-Tau averages. In the table on the left, we can see the results for the BiLSTM, and on the right, those for the Distilbert model. For the BiLSTM model, the correlation with the feature importance methods is high only when used on single sequence tasks. Agreement is much lower for the pair sequence tasks, and lower still for the attention mechanism. For the Distilbert model, agreement is low everywhere, regardless of the task. So what does this tell us? Well, that depends on the assumptions we are willing to make. If we assume the existence of a single ideal explanation, at most one of the explainable AI methods has found it. Under this assumption, the explanations produced by these methods are too different for all of them to be ideal. But is this assumption valid? For example, what if many rankings of the input tokens are all equally valid ways to compress a large model's prediction process into a single ranking? We ask ourselves, are most of the methods wrong, or is the assumption of a single ideal explanation wrong? Since it seems conceivable that the assumption is wrong, we interpret our results as evidence against it. We must conclude that agreement is not suitable as a method of evaluation. Therefore, we recommend using different, theoretically motivated ways to evaluate explainable AI methods. Agreement can still be useful in other situations, of which we give an example in our paper. In future work, we want to measure the agreement between the top K of rankings only, and we also want to measure agreement with human annotated rankings. Finally, we want to measure agreement with rankings that take into account the pairwise interactions that may occur between tokens. Thank you for listening. If you have any questions or comments, we would love to hear from you.